Hello, everyone. Welcome to this session. I'm very excited to be here for the second time in Austin, actually. I was here last year for DevOps Days in the same venue. Today, I'm going to talk about something I really care a lot, which is how to stop over-provisioning your pods to solve the initial spikes you may have with different kind of application runtime. In this case, we are going to use some example using the JVM. We are going to see one of the newest graduated feature for the Kubernetes project, which is In-Place Pod Resize. And we are going to see 4 different implementations of this feature. This is me. It's not AI. It's a couple of years ago and a couple of pizza ago too. By the way, I am Graziano Casto. I'm based in Italy. That's why I have this weird name. I'm a DevRel engineer in Akamas, an Italian company, an Italian startup doing software for the cloud native application optimization on Kubernetes. I'm community-wise, I'm also a tech lead at the CNCF TAG Developer Experience, and I am a Kubernetes Release Team member since 1.34. By the way, before I could jump directly to the implementation, but I worked a lot on this market research, so let me show it to you. So why we should care about the problem that the JVM has at startup in the pods? Because actually more than 75% of the users out there, especially in industries like banking or healthcare, are using the JVM to run their workload. Here on the QR code, you can find a market research I did a couple of months ago based on real conversation from 55 companies across EU and US. This is just one of the takeaways, which is the application runtime, but you can find also other cool stuff like how they approach the optimization stuff on Kubernetes and how deep is the optimization strategy in these companies. This is how most likely your JVM pods look like on Kubernetes. You have this resource spike on the CPU side. Why? Because the JVM has a couple of things called JIT compilation, which is just-in-time compilation, where your code is actually compiled on the startup. Then there is also the GC cycle that could compete to these spikes. But when the JIT compilation ends, you have a steady state that is much lower than the initial spike. So we usually size the container with the request for the CPU to afford this spike. But then we have a lot of wasted resources in terms of CPU when the steady state is reached. Why this is a problem? Because if you have, like in this example, a pod that is provisioned to 1.5 core and your steady state is 300 millicore, you basically are wasting 80% of your provisioned CPU. And this is not too much for one pod only, but if you consider 2 different scenarios, one with 10 services and the other one with 50 services, you are basically wasting a lot of CPU. How we can solve this problem? We have basically 2 options. The first one, which is the one we are going to talk about today, is considering only the Kubernetes layer. So we we know that we have the spike. We saw that how can we use Kubernetes only to decrease the request for the CPU after the warm-up is completed. The second one is more complicated, let me say. It's more about how to tune the JVM itself to reduce the spike. I will focus on the first one, but by the end of the presentation, I will talk about the second one too. This mechanism, this feature that helps us to resize the CPU, actually the memory too, for your pod is called In-Place Pod Resize. It is a feature that was graduated to stable in 1.35, which was the last Kubernetes version. Now we have 1.36 that was released a couple of weeks ago. And it was introduced in 1.27 and graduated to stable in 1.35. So it was a very long journey to graduate this feature. You can find here a very cool blog post on the official Kubernetes blog that explain all the changes made made from the beta version to the stable version. What is In-Place Pod Resize? To keep it simple, In-Place Pod Resize makes your CPU and memory attributes on the pod mutable. So it means that you can patch your pod directly at runtime, and using C group v2, actually, this is the dependency, you can't use it using the old version for the C group. You can update the resources, memory, and CPU only for your pod without restarting the pod. How it works? You, the user, ask for a resize to the API server. The API server itself performs a validation to understand that you are respecting the quality of service of the pod. The kubelet actually communicates to the CRI, the container runtime, to update the resources on the C group, and the pod is updated and the state is reconciled back to the API server. If you want to know more about how the different Kubernetes components work together to make it happen, this is another blog post written by one of the contributors that explain all the history behind this implementation, starting from the alpha stage to the graduation. Now, it is cool because allow you at a pod level to resize your pod, so to change the quantity of memory and the quantity of CPU, but you need to understand what you are doing, because it works at a pod level, but if you are using JVM, for example, you can use it to resize the CPU and everything is working properly. But if you are trying to update the memory, for example, the JDK itself calculates the memory at the start time. So you are just updating the box, but the JVM inside the box, which is the container, is running with the old memory. So you still need to update to restart the container to update the max heap size. This is a screenshot from one of the enhancement proposal into the OpenJDK. So they are proposing and they are starting working to have an automatic heap sizing for at least the G1 ZC. If you want to know more, the OpenJDK runs almost like the Kubernetes project, so you can enter this QR code and read the entire proposal for this new feature. So before going deeper into the different implementation, let's see how the entire picture looks like. The entire solution have 5 different phases. The first one is the creation, when you start up the new pod. The second one is the just-in-time warm-up, when you have the spike. Then all the implementation we did interact directly, listen to directly the readiness probe for your pod, and use the In-Place Pod Resize, the resize sub-resources, to update the resources and scale the available requests. But there is a problem, because to do that, one thing that is very important is to have a good timing into the downscale, because if you downscale too quickly the pod, you risk to throttle the service, because you are removing the CPU resource when the service needed, for whether it is for the JIT warm-up or for a traffic spike, for example. So we are going to see how different implementation deal with this shrinkage trap, let me say. So first implementation. One thing first. In-Place Pod Resize is a feature that acts at the pod level, but you are declaring your resources on the deployment level, okay? So I actually did a post on LinkedIn when this feature was graduated, and one of the main objections was, okay, it's beautiful that I can change the memory and the CPU on the pod, but I'm declaring memory and CPU on the deployment. How can I deal with that? The point is that this feature is not meant to change how you declare memory and CPU. This is a patching system that allows you to change memory and CPU on the fly when you need it. So these are 4 different implementations that show how you can solve the problem we saw earlier using In-Place Pod Resize. The first one is the easiest, which is a deployment. We are basically using the same test application, which is a Java application, a pet clinic application, which is a common Java benchmark, built using the JDK 25. I may need to update it since we have the 26 now. By the way, this first implementation is a deployment, basically. Is a kubectl pod that load inside from the config map a bash script that is running, that run all the commands needed to patch the system. How it works? This is the, on your right, you have the pet clinic deployment. We added basically a label to allow the controller, the resized deployment to find which application need to be resized. This label is startup boost enabled. And then we have the other deployment, resizer controller deployment, which is basically our implementation for the In-Place Pod Resize. As you can see, I'm using a kubectl image that loads controller.sh. This controller.sh is basically bash script that runs this kubectl patch pod sub-resource resize. Sub-resource is something added by the In-Place Pod Resize. Is where you are actually perform the patch and allow the C group to resize the actual resources allowed to the application. Above, you can see the resize policy. The resize policy must be added to the deployment to tell, okay, when someone wants to change the resources for these resources, actually the CPU, because we are working only with the CPU, an update is not required. So when you run the kubectl patch pod blah, 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 the C group automatically update the available CPU without restarting the pod. These are basically the 2 things that you need to know to use the In-Place Pod Resize. How to target a pod, an application for the In-Place Resize, and the second one, how to patch the application. The second one is quite similar. Okay, we now have the deployment with the kubectl pod and the script. How I can bring it into a sidecar? The difference is just how to deploy it, and if you do the sidecar, you don't need to label the pod because your sidecar is running and sharing the same context of your application. What are the different? First, as I said, the sidecar itself is running with your pod, so you don't need the label to select which application need the resize. There is a difference in timing because your application could be ready, but your deployment is not. If you are using the sidecar implementation, both pod and sidecar are ready together. So it's better in terms of sync between the resizer and the resized resources. The sidecar itself is self-contained, so your application and your resizer are actually coupled together. And the difference here is that if you need to resize only one application, you can afford to do a sidecar because the sidecar and the application are coupled. If you want to resize many applications that lives in the same node, it's probably better to have a sort of deployment or Kubernetes operator, as we are going to see later, because with the same deployment, you can manage different applications. And you can also have less overhead on infrastructure, because if you are resizing, let's say, 10 applications, you need 10 different sidecars running on the node instead of one. The other one, the Kubernetes operator. Everyone know what is a Kubernetes operator, right? Nice. Basically, the Kubernetes operator extend the Kubernetes features, the Kubernetes API, and allow you to create a CRD, custom resource definition. We did exactly the same thing. We are creating a startup boot policy, which is CRD, that allow you to create this policy in terms of, okay, my steady state want to be 300 millicores and target this application. What is the difference between doing Kubernetes operator or the deployment? The difference is that you are extending the capabilities of Kubernetes and you are getting all the benefit that you have with proper APIs inside the Kubernetes, which are a way to actually describe the state, to observe the state. You have a proper CRD, which is a proper API, so you can get all the available policy into the cluster, and you can describe them to understand, okay, this exact resources was patched, was resized when. This thing you can't do that with the deployment, for example, at least if you don't want to patch also the labels to have a timestamp for the resize. How it works? We did this startup boost policy. You are basically targeting using the match labels the application, which is the pet clinic pod we are using from the first implementation. And you are saying, okay, for the Kubernetes pet clinic application, I want to patch the container called pet clinic again, and my target CPU utilization is 300 millicores. As I said, using an operator, you can describe and get all the policies you have, and you can also get all the information about how the operator is behaving. So, which is the pod which are the pod that is targeting, the phase, and when it was resized, for example. Again, another comparison, which is the difference between operator and deployment. With the deployment or sidecar, which are basically similar implementation, you are doing a polling over the readiness probe to understand when the pod is ready. The operator acts a bit different because it's listening to the events for the pod, so the resizing is quite immediate. You don't need to poll the readiness probe every time to understand, okay, it is ready or not. Again, it is not self-contained. It's not coupled to a specific pod. You can handle many different applications with the same operator. How you can add a workload? If you're using a sidecar, you need to inject the sidecar into your application, and for the deployment, you need to add a new label on the deployment. So you need to change the actual target application manifest. For the operator, the application itself is completely agnostic in terms of how it works, because you just need to create a new CRT. Next one. The next one is the vertical pod autoscaler, VPA. Everyone knows what is the VPA here? Okay, nice. VPA has two are the main one, but three different components. The main one are the recommender and the updater. The recommender is the one looking to your metric server, your Prometheus, whatever, to understand the resources used and give you back a recommendation. The updater is the one that perform the resizing. The VPA works a bit differently because with the operator and the other implementation, you said, okay, just resize for the warm-up. You don't need to do anything else. The VPA is continuously looking to the metrics of your services and perform recommendation over time. So it's, let's say, extended into how it works. To configure the VPA is quite simple, quite similar to the HPA, for example. You have to to declare an update mode for the update policy, because otherwise the VPA perform the resizing and restart the pod. In this case, we are using the in-place or recreate policy, which use under the hood the in-place pod resize. And you need to declare, to define, two boundaries, which are the minimum allowed and the maximum allowed for the CPU in this case. And this one is an example of the recommendation you get. So you say the container name, the lower bound, which is your min allowed, your target, which is the amount of CPU that will be used for the patching, the upper bound, and uncapped target. Uncapped target is to observe the state, but they can't add 35 millicores because our min is 200 millicores. What's the difference? The other one are based on the polling architecture. This one is based on the VPA. So for the other one, you should decide which is the steady state, which is the target value for the CPU. This one is more data-driven. The resize latency could be minutes because the VPA is based on historical data, so you can't actually be sure of when the resize will be done. To add a workload, you need to create, as for the operator, a new VPA object, and the infra overhead is just the VPA components. Now, as I said, the VPA is working more widely on the workload. One thing good to know is that I think SIG scheduling, so if I'm not wrong, is working on a new feature for the VPA, which is the CPU startup boost, to use the VPA exactly for this implementation. So the VPA is working just to resize the peak of the warm-up and not the entire life cycle of the application. If you want to know more, the enhancements for the Kubernetes are described on on GitHub, So you can scan this QR code and access the description of the enhancement. Now, you can trust me, but you can also try the demo on your device. This is a GitHub repository where you can find all this implementation with an explanation of how they are working together. You can scan it, or you can download the slide later. Now, last thing. Okay, I know how to work only with the Kubernetes layer. How I can mitigate the startup spike at the beginning. So how I can act on the JVM to resolve this problem. The point is that when it comes to the optimization, is always a layered problem. We focused on the pod side, so only on the Kubernetes side, but you can also deal with the application runtime to optimize together the things and get a better result. Then you can also, for example, if you're using the VPA, it's a bit tricky to make the VPA and the HPA work together. So you can understand how to make the right size at the beginning and then scale horizontally, for example. Or you can also consider the nodes. Which hardware are you using in terms of cost? If we are focusing on the warm-up spike for the JVM, the main actor here is the JIT compilation. The JVM is a complex system, and the JIT compilation is one of the phases into the warm-up. As a complex system, you have something like 800 different parameters for the configuration, just like the max heap size, for example. For the JIT compilation, you can use these four to govern how the JIT compilation works, because the JIT compilation has 4 different states, and you can govern these different phases using this configuration to say, okay, I don't need the C2 level of compilation. You can stop earlier, and so you are consuming lower CPU to perform this kind of compilation. You can read more about the pitfalls of Java in Kubernetes. I wrote an article about that if you want. Now, this is an example of a performance study we did on the same application, considering together the pod level and the JVM level. As you can see, we have basically the same throughput, which is the red line, and we were able, configuring the HPA, the pod resource and request request limits for GPU and memory, and the JVM itself to lower a lot the latency, which is the blue line. We went from 240 milliseconds as a spike to less than 5 milliseconds. And in terms of resources, this is the same time window for the analysis. We had lowered a lot the number of replicas, moving from 15 to only 1. Basically, the HPA here is not working. And the overall CPU usage in this case, which is the yellow line, is decreased a lot from from 6 core, 6 CPU to less than 2, 1.5 more or less. So 48% less CPU used. I finished the presentation. If you have any questions, just ask. Here you can find the slides. You can download the slides with all the previous links, or you can reach me on LinkedIn or my personal website or my email if you prefer. Thank you so much, and if you have any question here, thank you.